Hey, hi, everyone. So we will discuss today. We'll study, not discuss. I think to discuss this is a study that is very clear. We are not having any discussions or especially teachings with anyone, but we'll go through ELMo embeddings, which is very interesting and very important. Especially this is the first embedding which brings in word variations with respect to context. So word to back, fast text, glow and stuff. What we have observed is they consider context, but they consider um, word in different contexts, and then they come up with one single form. But what we are talking about is um, a word it could have different meaning in different contexts, and how does the system understand that how can it understand saying same word being there in different places and having different contexts should be understood is the objective. So let's see how Elmo is gonna do it. We'll go through some videos and blog posts today. We'll just go through those videos and content today. There's not much of talking in this. Um, let's focus on that. So let's start off with this video. Let's see.
Into the rest of the model.
To use Proto Studio as an instrument plugin, navigate to the Fairlight tab, add a new stereo track, and rename it.
This is not a simple embedding layer. Instead, ELMo uses character-based word representations. Here's broadly the way that looks. Our inputs are given to us as a sequence of words. We break these words up into their individual characters. The characters are fed to a character embedding layer. So for every character, we get an embedding vector. The sequence of these embedding vectors representing one word is fed to a set of convolutional neural networks, each with a different kernel width. These are combined and max pooled over the time dimension, and this resulting representation of the word is fed through two linear layers, each with a highway connection, which is a bit like a residual connection but parameterized. And from this, we get a word representation. Now, the benefit of this is that our word representations are character aware, so that if we see a new word that we haven't seen before, and in realistic natural language settings, this is a very important property because a lot of the text that you're going to encounter may be misspelled. So, for instance, if you misspell the word accommodations, it will still, in terms of its characters, look a lot like the correctly spelled word accommodations. So the embeddings will still be close together. So this gives us our non-contextual word representations. These are then fed into a sequence-to-sequence model, which brings us to probably the main innovation of ELMo, which is that it uses bidirectional LSTMs. So we built two multi-layer LSTMs, one that reads the sequence forward and one that reads the sequence backwards. And this, because LSTMs are causal models, this ameliorates the problem of only being able to look at the sequence in one direction. So both of these models produce contextual word embeddings, one based on the left context of the current word and one based on the right context of the current word. Now, the question is, how do we train this model? We can assume that we have a large amount of natural language, but no annotations. So putting these two together gives us a full model. We have a character-aware token representation. The tokens that result from this are fed to two multi-layer LSTMs. So now we need a way to train these LSTMs. And that is done by treating them as language models. We've seen the basic principle before. We called it autoregressive modeling then, but it's worth putting it into slightly more precise terms. A language model, in its most basic definition, is a probability model of language. It's a probability model that assigns a probability to a particular sequence of words or characters. We'll look at a word level sequence to explain the principle. So what we want is some probability distribution that will tell us how likely a sentence like this is to be encountered in a given setting. And the first thing we do is we break up the sentence into its tokens, in this case words, and we treat each of them as a random variable. So word 1 through word 6 are random variables, and these can each take on as their value one of the words in our vocabulary. And what we're looking for is the probability that the first random variable takes on the value congratulations, the second variable takes on the value you, and so on until the sixth random variable, which should take on the value prize. And in shorthand, we will write that like this. Now, we don't usually have enough data to see even one complicated sentence multiple times. So what we need to do is break this probability value at the bottom up into multiple component parts based on conditional probability, which we can then estimate. And to do this, we will use this property of probability, which is simply if you take the definition of conditional probability, you can rearrange it to get this. So the joint probability of x and y is equal to the probability of x conditioned on y times the probability of y. And we can apply this principle to decompose a probability for a sequence of random variables into a product of multiple conditional probabilities. That looks like this. We start with a sequence of random variables as before. We rearrange the random variables from last to first, which doesn't change the probability. And then we simply apply the rule that we saw in the previous slide first to the random variable w1, which looks like this. And we apply the same rule again to the random variable w2, which gives us this, and so on, until we've decomposed the whole joint probability into a sequence of conditional probabilities. Now we can do this in any order, but if we stick to the order in which the random variables are given, the natural sentence order, what we see is that we get a sequence of conditional probabilities where every word depends conditionally on the words that occur before it. So the probability that we're now looking to model is this. The probability of seeing a particular word, in this case prize, given that we have seen the words before it, in this case, congratulations, you have won A. And if we can model this probability, then we can multiply all the probabilities that it gives us to give us a complete probability of the joint distribution. So in logarithmic terms, the log probability of a sentence is the sum over all log probabilities of the words in the sentence conditioned on all the words that came before it. And if you think back to what we talked about in the first slide, autoregressive modeling, you'll note that if we train a sequence-to-sequence model like this, we feed it with a particular input and we train it to predict the next word at every time step by giving it as a target value input shifted 1 unit to the left. If we train our neural network like this, we have an output layer over the vocabulary that is softmaxed so that it gives us probabilities over the vocabulary. We can interpret every single probability vector that this output gives us as the probability that we'll see a word given that we've seen the words that come before us. So the vector indicated here gives us the probability of seeing the word on, given that we've seen before it the words the, cat, and sat in that order. So to summarize, if we train a sequence-to-sequence model autoregressively with a softmax output layer, what we get is a conditional language model. Now, this might just seem like a fairly simple statistical model that would be easy to train, but it actually turns out that if you look at what a perfect language model needs to be able to do, it captures not just syntax, not just grammar, but also semantics. For instance, if we see the sentence, the man fell out of the, there are different ways of completing this. And even a very simple language model can tell us that cycling does not fit grammatically, so it should get a very low probability. But it requires quite a sophisticated language model to choose between the options window, aquarium, and pool. They all fit grammatically. They're all nouns, and this sentence is completed by inserting a noun phrase. So a language model needs to have a certain kind of grasp of semantics and common sense in order to know that a window is much easier to fall out than an aquarium, and it's much more likely that people fall out of windows than out of aquarium. And if it's a particularly sophisticated language model, then it can even tell you that a person is more likely to fall out of an aquarium than out of a pool, even though both are so unlikely that these things have never been mentioned before in the corpus, that the model has never seen something like this described in the data set. if it contains a certain amount of common sense and knowledge about the world, then it can reason that at least an aquarium is something you could technically fall out of, whereas most pools, it's actually impossible to fall out of because they are embedded in the ground. So all of this is just to say that a language model as a task, getting it absolutely right, is what we call AI complete. You need a complete understanding of the world and a complete intelligence in order to model the language completions correctly. This isn't practically true, but there are a lot of models these days that are coming pretty close to this sort of thing. So, putting all of that together, this is what the ELMo model looks like. We are given a set of inputs as words. These are broken up into characters and fed to a CNN embedding layer, which gives us non-contextual vector representations of these words. These are fed to two separate LSTM language models, one which reads the sentence forwards and one which reads the sentence backwards. And both of these are trained separately as language models. How do we then take the resulting model and do fine-tuning? We take a weighted mixture of all the word embeddings produced in this ELMo model. So the ELMo model produces first non-contextual word embeddings, which we've called H init. For every word K in our sequence, we get a non-contextual word embedding HK init. And then for every layer in this forward LSTM, we get a contextual word embedding. And for every layer in our backward model, we get a contextual word embedding. So the way ELMo now allows you to fine-tune this is by summing up all of these contextual and non-contextual word embeddings in a weighted sum where the weights are parameters specific to the fine-tuning task. So all the purple values in this formula are values that are learned specifically for the task we are fine-tuning for. And then the contextual word embeddings, EK, that follow out of this are fed to another sequence-to-sequence model that is designed specifically for the task. And we won't go into the details here, but the paper outlines a large number of tasks on which it evaluates the performance of ELMo, and for each task, a very particular model is designed to solve that task. And these are the main results presented in the paper. So on the left, we see a number of tasks, like Squant, for instance, is a natural language answering task where a small snippet of Wikipedia text is given and then a question is asked in natural language about that snippet of text. And the rest of the tasks are similarly hand-annotated, manually curated natural language processing tasks. And the main result from the paper was, first, that if we start with a baseline and then give that baseline instead of randomly initialized basic embeddings, we give it the ELMo embeddings, the performance improves massively. And the second conclusion is that the performance improves so much that on each of these 6 tasks, the resulting performance is state-of-the-art, is better than the performance that was up till that point could be achieved. So that's ELMo. It's a system that does large unsupervised pre-training and that allows small-scale supervised fine-tuning. It contains as its basic structure a bidirectional LSTM, but it does still require elaborate fine-tuning architecture. So the architectures that achieve this kind of state-of-the-art performance on all of these tasks are still quite elaborate LSTM structures. However, what we see later after ELMo with these successor models like BERT and GPT, that this pressure reduces, that the better the pre-training model becomes, the simpler we can make our fine-tuning architectures, to the point where in most cases nowadays we can simply add one fine-tuning layer on top of our pre-trained model, and that's enough already to give us a very good performance. And we'll look more into that in lecture 12 when we start investigating self-attention.
It's very nice. This guy is actually explaining it pretty well. Good programming. LSTM, CNN. What to echo? Okay.
Hello, everyone.
Deep generative modeling.
Hello, everyone. So today we'll continue with deep generative modeling, and we'll move to the next class of generative models, namely implicit models. So a quick recap from the last lecture. So we divide
Okay, let's go through this once to understand. Other text models can be used to perform inference. So, it just doesn't say much. It says simply going in that direction. Mm,
In the last, what you need is ameliorates the problem of probability of x conditioned on y times the probability. Now, this might just seem like a
Let's test this. Oh, I will type this as well. Do I have transform system? I'm trying to run this program. Oh, parked ELMo model should be downloaded. Hmm. It's like he's trying to use ELMo embeddings and to prove that ELMo embeddings are doing better than normal basic embedding. Um, when he says basic embedding, what was he using? Mm. This one. Okay, so we'll go back to the system. Okay, so uh, ELMo embedding models are pre-trained and they are available online. Looks like there are different variants of ELMo embedding. There should be somebody who should be owning the ELMo embedding model, right? These guys, oh, Alpha TF Google. Oh, very Google is publishing. Let's see that. No explain that. No, okay. So Allen Institute is the main one. Hmm. behavior models. Developer model has a corresponding model card in the this model also has దీంట్లో ELMo పేర్లు రాశాను మ్యామ్. I'm trying to work with development, getting over the time out. Sometimes I have to. Oh, three. So it is presented by of size 1024 dimension. That will be SDLCR. And I'm adding total between four data. Is because it's pre-trained model, the embeddings are always in my birthday is my birthday. Okay, let's let's test that. Input answer. What is that sentence? He said, I should bring this here so that people will also look at it. I am testing with two sentences. One is my kid is here. My kid dusted this place by spilling soil, and I'm assuming it's in order 1, 2, 3. I'm picking up the third uh, word embedding. This one, I'm just pasting it here. I'll drop it back and paste the whole thing here. I can also make so two, two, two. I just go. See, they're different. This 5, 1, 2, 3, 4, 5, and this one is yeah. The tested word meaning is different in different. This is good. So contextual word embedding is working in scenario. Okay, let's stop sharing. So that's it with ELMo today, guys. We'll connect more tomorrow. Thank you.